Okay, so for FRQ1A, we're gonna first draw the free body diagram. So we're gonna draw the block, so big M, which is the one that's sitting on the surface. So first there's an Fn countered by of Fg of the same magnitude. F of G. And then pulling it towards the pulley is T. And then for the next block, which is the hanging block, small m. So first there's an Fg right here. But then we also have a T, which in this scenario should be smaller than the Fg. Because if you look at the line of motion of this, so this T is going to be smaller than Fg. Because then the line of motion will be going, for the hanging block, will be going down. This one will be going to the right. And then for 1b, so we know the net force of the system, we could write as m small m plus big M times A cis. Or we just write, well, A cis in this scenario. So the A cis, so the only other force in here, that's pulling it down, that's acting on these blocks, are the T and Fn and G. It has actual value is the Fg of the hanging block. So Fg of H is equal to m plus big M times A cis. So if you isolate A cis by divided by m plus big M, so Fg of H, which is the hanging block, over m plus big M is equal to A cis. The FGH here is just a small block to multiply by gravity over m plus big M is equal to A of the system. And that will be our acceleration of the system. So for 1c, we're going to do the net force of the hanging block, which in this case is m A cis. And then net force of the hanging block. So we know that the line of motion is going to be going down the block, or down the platform. So it will be going downwards to the bottom of the page. So then we know it's going to be Fg minus T is going to be trying pulling against it, but Fg is bigger, is equal to small m A cis. So now we're going to try to isolate for T. So I'm going to move m A cis to this side. So Fg minus m A system is equal to T. And then we can expand this one right here. So then Fg is just mg minus ma system, which is equal to T. And that will be that'll help you calculate the tension. And okay, so for 1t, if we increase m new is greater than m old, then what will happen here? So we're gonna look at the A cis function first. So A cis equals mg over m plus big M. When we increase this right here, this denominator, the big M, this denominator here will get actually bigger. And because this gets bigger, that means this whole fraction right here is going to get smaller. So as m increases, that means A cis is going to decrease. Now, in contrast, we look at T. So we know T is equal to mg minus ma cis. So if we look at here, A cis here is going to be smaller if big M gets bigger, right? And since small m and g are going to be remain the same, that means this T will become bigger because m A cis will become smaller due to A system becoming smaller as m gets bigger. So T increases as big M increases. And now we are okay. So for 1e, we're going to try to find the acceleration of the system. So net force of the system is equal to m plus big M times A. Now we got two different things. So first we have Fg of H, the hanging block. But now, because there's friction involved, we have Fk, the big block, is equal to m plus M times A. Now we can isolate for A here by dividing it by m plus M. So Fg of H minus Fk of M over m plus big M is equal to A. Now in this scenario, Fk, so first mgh will be just small m times g minus Fn times mu of k over M plus big M is equal to A. Now in this block, the only vertical forces that are acting on it for the one that's sliding is just gonna be Fg, because then if we look at the net force in the y direction, which is equal to 0, because it's still on the ground at the moment, so it's gonna be equal to Fn minus Fg, and that means Fg is gonna equal to Fn. So I can plug it back into here. What is gonna be Fg M. This is all big M. So now we see mg minus Fg of big M times mu k over M plus M is equal to A. And we can expand this to small mg minus big Mg mu k over small m plus big M, which is all equal to the acceleration of the system. Okay, so for part F, what we're trying to find is T. So I'm going to take the net force of the hanging block, which in this case is going to be Fg minus T, which if we take the net force, it's just small m times A of system, which we found earlier over here. And then next, we're going to isolate for T. So we say, I add T both sides and then subtract MA system. So we have T is equal to Fg minus MA of system. So we can expand them. So Fg in this scenario is just small m times G minus small m. And then A system is what we found earlier. So small m times Mg minus big Mg mu k over M plus big M. And that will be our T. Okay, so for T Frq, which is what we found in 1F, that was equal to Mg minus small m times Mg minus big M G mu k all over M plus big M. And the original one for T without frictionless, what we found was Mg minus M times Mg over M plus M. And that was the tension we found earlier. So when we compare these two values, so we look at, they both have an Mg right here, but we have to look at this. So what we see here is we have M times Gm minus Mg mu k over M plus M. The only difference here is the numerator, which is Gm minus Mg mu k in contrast to Mg. And since we're subtracting by a value here, this will be less than its counterpart, Mg, because we're taking that same value, but we're subtracting by another value. And as a result, because of this, that means since this will be less than this, and these are the same, therefore, the T Frq here, and the frictionless, will be greater than the original T when there was no friction involved. Okay, and then for the next one, 1H. So we're gonna draw a free body diagram. So I'm gonna first start with the big M that's still on the platform. So there's gonna be an Fn, which is gonna be equal to the Fg here. But then now we know the line of motion is gonna be to the right. So we'll be moving to the right. That means friction will have to be this way. But then we have another block that's pushing against it, so it will be pushing onto the block at F small m of big M. And this will also be pulled by T, which is pulling towards the pulley, which is to the right. And then next we're going to work with the small m that's going to be on this platform. So also have an Fg. I'm going to put notations here. So M, M, M. This one has FGM, which will be smaller than this, unless it's bigger than Fn of M, small m. And then next up is going to be a Fk of M, Fk of M, because it's trying to move to the right, so the friction has to pull it to the left. And then finally, there will be the force of this block onto this block. So it'll be here, and that'll be F of big M on small m. And then finally, we have the hanging mass, M. The only forces here is going to be the tension. We're going to try to pull it up, but then it's going to be going down unless the tension equals out to the FG. But in most scenarios, it's probably going to be going down. But it depends on the situation. And this would be our free body diagram for this. Okay, so for 1I, so we're going to first write the net force of the system, which is equal to Fg of the hanging mass minus the Fk of the combined mass of the two blocks that are on the platform. Since they're on the same platform and they're touching each other and they're moving together, we're gonna combine both of their masses together to simplify the question. So we can say net force of system, which is just big M plus small m times A of system is equal to small m times G minus, in this case, Fn for both the blocks. So we look here of y for m plus m, and that will be equal to 0 because it's still on the platform, which is Fn minus Fg because there's no other vertical component. And then that means Fg of m plus m is equal to Fn of m plus m. I'm going to put it here too. And so that means we're going to combine this, so it'll be m plus m times g, which represents Fg, times mu of k in this scenario, because it's just Fn times mu k. And then now we're going to try to solve for a system. And so we're going to divide it by this. So a sys is equal to mg minus big M plus small m times g mu k over m plus 2 of the small m, lowercase m's. And we just plug numbers in. So we know the small m is equal to 3 kilograms times 9.8 force of acceleration due to gravity, minus big M, which is 2 kilograms, plus the 3 kilograms times acceleration due to gravity, times mu k, which is 0.18, all over 2 kilograms plus 2 times 3, which is 6. And as a result, the A system will be equal to 2.57 meters per second squared. And this will be going in the line of motion. So in this scenario, it'll be going, the hanging block will be continuing down the page. Now for 1J, we're trying to find the tension of it. So net force, so remember this, net force of the hanging block is equal to the force of gravity of the hanging block minus T. We can isolate this, so T is equal to Fg of H minus net force of Fh. As we did earlier, this will be small g minus of small g, so it's small m times A of system. And the A of system that we had from this was 2.57 meters per second. So I'm going to start plugging numbers in. T is equal to 3 times 9.8 minus 3 times 2.57. And then as a result, your T should be equal to your tension in the rope, which should be equal to 21.682 newtons. Now we'll be pulling it upwards. So for 1K, I'm going to use the net force of the smaller block, the small m, because then it doesn't have it has less force to act on it because the other one has a T on it. So in this case, it will be F of the big block on the smaller m minus the friction of small m. And so we're going to try to find the contact force. So in this case, this one right here, the net force, will just be small m times A of system. And then we're at Fk of H, of m, my bad. It's equal to F big M on small m. And so what happens here is now we're expanded, so m A sys like normal, but then this Fkm is just gonna be so Fn in this scenario will just be mg, because if we look at this again, a small m, it would just be Fn minus Fg, which is equal to 0, and then Fm is equal to Fg in this scenario for the small m. So it'll be Fn times small m times mu, and we know F, so it'll be Fg of small m times mu k, and then we know that's equal to F of the contact force between the two of them. And we start plugging numbers in. So small m is 3 times 2.57 meters per second squared, plus that's 3 times 9.8 because of g times mu s, oh it should be mu s, times 0.18 F big M on small m. As a result, our answer should be 13.0095 newtons, which is the contact force between the two of them. And in this scenario, it'll be going towards the line of motion. And then for 1L, we could easily just use common form for this. So VF squared minus VI squared is equal to 2A cis in change in Y, VI of M of H, which is a hanging block. So we know the VI is going to be just 0. So that cancels out. And it's 2 times 2.57, which is the acceleration of the system, times negative 20, because it's going to be, actually it should be positive in this scenario. It could be just be positive 20, because we factor in this line of motion here. This will be in the same direction as this, so we just say the line of motion is just going to be positive for this one. So then we can square root this, and our answer of the hanging block, it should be 10.144 meters per second in the line of motion. So we plus, because that's in the direction of the line of motion. Then for 1m, we're trying to find t, which is just vf, which is the change in velocity. So vf minus vi of h over a is system. And we know vih is 0, but vfh is just 10.144. This and divided by 2.57, which is our acceleration of the system. And as a result, your answer should be 3.94 seconds. And then finally, we're doing 1n. So in this case, we're going to draw a of t. We're going to sketch out a of t. So a meters a second squared, and then t is just seconds. In this scenario, it's just going to be a horizontal line because of the constant acceleration. Next up, we have net force. So net force of F is the system. Net force, which is just in newtons, and T, which is seconds. And since it's just mass times acceleration, it's going to be a similar thing, except that the horizontal line will probably be amplified by the mass of the block, or the system. Next up, we have velocity. So here you have v, which is meters per second, and then t, which is seconds. And since this is acceleration, that means the v is going to be increasing at a constant rate, hence this. And then s, which is also meters per second, and t, which is s, which is seconds. And since it's still going in line of motion, it hasn't changed direction. I could just redraw the same one, and it should be a straight linear line. And then finally, we have x. T represents seconds, and x represents just meters. And so what we know about this is that it's a concave up, and it's always increasing. So then because it's concave increasing, I'm going to draw half a parabola that's going to be concave up and increasing. So it should look like half of a U. And this will be going on until it reaches the block, the ground. And these are our graphs.